The universe in a blink. What is cosmic inflation? Have you ever wondered how our vast universe, filled with billions of galaxies, stars, and planets, could have emerged from something almost infinitely small? One of the most fascinating and mind-bending explanations in modern cosmology is a phenomenon known as cosmic inflation, a brief moment in time when the universe expanded faster than the speed of light. According to this theory, just a tiny fraction of a second after the Big Bang, around 10 to the power of minus 36 seconds, the fabric of space expanded exponentially. In that unimaginably short moment, the universe grew from a subatomic scale to a macroscopic size, inflating by a factor of at least 10 to the 26th power. To put that into perspective, it is like a balloon expanding from smaller than a grain of sand to larger than a galaxy in less than the blink of an eye. This concept, though hard to visualize, is central to our understanding of the early universe. It helps explain why the universe looks the way it does today, remarkably uniform in all directions, yet filled with the subtle fluctuations that eventually gave rise to galaxies and stars. The Big Bang theory itself was first proposed in the 1920s by Belgian physicist and Catholic priest Georges Lemaitre. He suggested that the universe originated from a primeval atom or a singularity. A few years later, Edwin Hubble provided strong observational evidence for this idea when he discovered that galaxies are moving away from us, implying that the universe is expanding. But there was a problem, even with the Big Bang model. Some aspects of the universe didn't quite add up. Why does the cosmic microwave background radiation, the afterglow of the early universe, appear so uniform, even in regions that should never have been in contact? Why is the geometry of the universe so flat? These puzzles led physicists in the late 20th century to propose something revolutionary: inflation. In the early 1980s, physicist Alan Guth Admit proposed the idea of inflation to solve these problems. He suggested that a hypothetical energy field, now called the inflating field, caused a brief but enormous expansion of space. This inflationary phase smoothed out the universe and stretched it so rapidly that even the tiniest quantum fluctuations were magnified into the seeds of future galaxies. This idea was later refined by physicists like Andrea Lin, who developed the concept of chaotic inflation, suggesting that inflation might not be a one-time event, but a process that could happen in different regions of a larger multiverse. In short, cosmic inflation provided a framework that explained the uniformity, flatness, and structure of the universe far better than the original Big Bang model alone. It also linked quantum mechanics, the physics of the very small, with cosmology, the physics of the very large. Today, although inflation is still a theoretical model, it has gained strong support from observations of the cosmic microwave background, particularly from missions like the WMAP satellite and the Planck spacecraft. These missions map the tiny fluctuations in the background radiation, and their patterns match the predictions made by inflationary theory. So, what caused the universe to inflate so violently, and how did it eventually stop? And what does this tell us about the true nature of reality? That's what we'll explore next. Quantum fluctuations, the engine behind inflation. To understand what drove the inflationary expansion of the universe, we must turn to one of the most counterintuitive and powerful theories in physics, quantum mechanics. At the smallest scales of reality, empty space is not truly empty. Instead, it is a seething sea of energy, constantly flickering with brief appearances of particle-antiparticle pairs that emerge and annihilate in a fraction of a second. These are known as quantum fluctuations. Now imagine these fluctuations occurring in the early universe, a time when energy densities were unimaginably high. According to inflationary theory, the universe was dominated by a mysterious energy field called the inflating field. This field had a very peculiar property. As long as it remained in a certain high-energy state, it caused space itself to expand at an exponential rate. Think of the inflating field as a kind of fuel source. While it remained unchanged, the universe kept inflating. But quantum mechanics ensured that the field was never perfectly stable. At some point, the inflating field decayed, an event known as reheating, releasing a tremendous amount of energy that formed the building blocks of matter as we know it: quarks, electrons, and photons. The fascinating part is this: during inflation, quantum fluctuations in the inflating field got stretched across space. Tiny, random fluctuations, smaller than an atom, were blown up to cosmic scales. These slight differences in energy density became the seeds for all large-scale structures. In the universe, later, gravity amplified these tiny overdensities. Denser regions began to attract more matter, eventually forming galaxies, stars, and planets. In other words, every galaxy we see today began as a tiny ripple in the inflating field over 13 billion years ago. This prediction, that the structure of the universe originated from quantum fluctuations during inflation, has been remarkably supported by observational data. The Planck satellite, launched by the European Space Agency, measured the cosmic microwave background (CMB) with unprecedented precision in 2013. Its results confirmed that the temperature fluctuations in the CMB matched the statistical patterns expected from inflationary quantum fluctuations. Moreover, the fluctuations appear to be nearly scale invariant, meaning their size is almost the same across different scales, a key prediction of inflation. This is one of the strongest pieces of evidence that inflation likely occurred. So to summarize, the wild idea that tiny quantum ripples and a mysterious energy field could grow to become galaxies and galaxy clusters may sound like science fiction. But thanks to precise cosmological observations, it is now a serious scientific theory with substantial support. Still, it raises deeper questions. What exactly is the inflating field? Is it related to other known forces or particles? And did inflation happen just once? Or is it still happening in other parts of a larger multiverse? We will explore these possibilities in the next part: eternal inflation and the birth of the multiverse. If the idea of the universe inflating from a quantum ripple sounds extraordinary, hold on, it gets even more mind-bending. The original inflationary theory proposed that inflation happened everywhere and then stopped. But in the 1980s, physicist Andre Linde introduced a new twist called eternal inflation. According to this model, inflation doesn't end all at once across the universe. Instead, it ends in pockets, local regions where the inflating field decays and creates matter, just like our observable universe. But surrounding these pockets, inflation continues. That means while our universe formed and cooled down, other regions of space may still be expanding, spawning new bubble universes. This leads to the concept of a multiverse, a vast, possibly infinite collection of universes, each with different physical laws, constants, and structures. Some might contain no matter at all, while others could have entirely different particles or dimensions. Our universe would be just one bubble in an ever-growing cosmic foam. The idea is hard to test directly, but it emerges naturally from the mathematics of quantum field theory and general relativity. When combined under inflationary models, the mathematics predicts not just one universe, but a self-replicating universe. In this scenario, space-time is like a fractal, constantly generating new regions where physics can vary dramatically. What makes this model compelling is not just its elegance, but its ability to solve several puzzles in physics. For instance, it helps explain the fine-tuning problem. Why do the constants of nature, like gravity, the charge of the electron, or the strength of nuclear forces seem precisely adjusted to allow life? In a multiverse, the answer could be simple. These constants vary in each universe, and we just happen to live in one where conditions support life. This is known as the anthropic principle. We observe a life-permitting universe because only in such a universe can observers like us exist. Some physicists have attempted to find indirect evidence for the multiverse. In 2010, cosmologist Roger Penrose and physicist Vivek Gharzadian claimed to find concentric circles in the cosmic microwave background. patterns they believe were echoes of events that happened in the universe before the Big Bang. Though controversial and later challenged, it sparked renewed interest in the idea that the Big Bang might not be the beginning, but a transition between cycles of cosmic evolution. Eternal inflation also raises philosophical questions. If there are infinite universes, does everything possible eventually happen? Are there copies of you, me, and everyone else living slightly different lives? While these ideas remain speculative, the concept of eternal inflation and the multiverse is now taken seriously in theoretical physics. Many leading cosmologists, including Alan Guth, Andre Lin, and Max Tegmark, have argued that it might be the most plausible explanation for the structure and nature of the universe we see today. But this journey into infinity doesn't end here. There is one more layer to peel back. What does inflation tell us about the beginning of time itself? What came before the Big Bang? The mystery of time is beginning now that we have a clearer view of inflation and the multiverse. A deeper and more haunting question emerges. What, if anything, came before the Big Bang? Traditionally, the Big Bang was considered the beginning of everything: space, time, matter, and energy. According to Albert Einstein's theory of general relativity, as you go back in time, the universe contracts until, at time zero, it reaches a point of infinite density and temperature. This is called the singularity. At the singularity, the known laws of physics break down. Time itself, as we understand it, ceases to have meaning. You cannot go further back because there is no before in the usual sense. The beginning of the universe is also the beginning of time. But modern theories challenge that narrative. In quantum physics, singularities do not sit well when gravity and quantum mechanics are brought together, as they must be at such extreme conditions. Something new emerges. One of the most influential attempts to resolve this paradox is the no-boundary proposal, developed by physicists Stephen Hawking and James Hartle in the 1980s. According to their idea, the universe did not emerge from a single point in time, like a spark from nothing. Instead, time itself is like a smooth curve near the beginning, more like the surface of the Earth near the South Pole. At the South Pole, all directions point north, but there is no south of the South Pole. Similarly, time has a rounded beginning but no boundary, no sharp edge that you can define as before. In this picture, asking what came before the Big Bang is like asking what is south of the South Pole. It is not a meaningful question, because time itself is part of the structure that unfolded during inflation. This theory is supported by quantum cosmology, which uses the tools of quantum mechanics to describe the birth of spacetime. Here, the universe begins as a quantum fluctuation from a quantum foam, a seething sea of energy and probabilities. From this foam, a bubble of spacetime, our universe, tunneled into existence. Another approach comes from string theory, which posits that fundamental particles are not points but vibrating strings, some string. Theorists suggest that the Big Bang was not a beginning but a collision, a brane collision, where higher dimensional objects smashed into each other in a pre-existing space. This would mean our universe came from an event within a larger, eternal multiverse. There are even models of cyclic universes, such as those developed by Paul Steinhardt and Neil Turk, in which the universe goes through infinite cycles of expansion and contraction. In such models, the Big Bang is simply the latest rebirth in a never-ending sequence. Though these theories differ, they share one radical idea. The Big Bang may not be the beginning after all. Instead, it could be a transition, a phase change, or a boundary in a deeper and more complex cosmos. Yet none of these models have been confirmed. The physics of the Planck era, the first 10 to the minus 43 seconds of the universe, remains one of the greatest frontiers of science. Our instruments cannot yet probe such extreme energies, and our mathematics is still incomplete. Still, by combining observational evidence from the cosmic microwave background with insights from quantum gravity, physicists inch closer to solving the greatest puzzle of all, not just how the universe began, but why there is something rather than nothing. And that brings us to the present day, a time when our understanding of the universe is expanding almost as fast as the cosmos itself. The end, or just the beginning, as we reach the end of our journey through cosmic inflation, quantum fluctuations, and the edge of time itself. One thing becomes clear. The story of the universe is far more mysterious, beautiful, and complex than we ever imagined. We began with a simple question: what is the Big Bang? And uncovered a chain of theories, experiments, and insights that have reshaped our entire understanding of reality. We learned that the Big Bang was not just a giant explosion, but the unfolding of space-time itself. We saw how, in a fraction of a second, inflation expanded the universe by unimaginable scales, setting the stage for all the matter and galaxies we see today. We explored how quantum fluctuations, the tiniest ripples in the energy of nothingness, may have planted the seeds for stars, planets, and eventually, us. We ventured into the mysterious before of the Big Bang, a realm where time may have no beginning, and the universe might be part of a vast multiverse or an eternal cycle of creation and destruction. And we discovered that, while much has been revealed, there is still so much we do not yet know. Every new telescope, every particle experiment, every equation written on a blackboard brings us a little closer to answering the greatest questions of all. Where did we come from? What are we made of? And what will become of the universe? These questions aren't just for scientists. They belong to all of us. Because in some deep and poetic sense, we are the universe trying to understand itself. So, as we continue to gaze at the stars, remember, each discovery is just a new beginning. There's always more to learn, always more to wonder, always more to explore. If you found this video fascinating, please give it a like. It really helps support the channel. Share it with friends who love science, space, and the mysteries of the cosmos. And if you haven't already, subscribe to Astronomical Library so you never miss a journey into the wonders of the universe. Thank you for watching. Stay curious and keep reaching for the stars. We'll see you in the next video.